This is a table saw. This is a lot of dust. This is an idiot. And this is the overarm dust hood I spent the last several weeks designing and building to hopefully correct all of that dust. So if you're curious to see how I did it, and if it even works, stick around. I started by getting my equipment moved into position, and to do a temporary mock-up of my plan. I'm a very visual person, and this allowed me to see it in raw form and get the needed measurements to be able to execute this. While I do that, let's go over my plan and idea. Starting with my criteria, and it's in no particular order because I find them all to be very important. CFM. To maximize the effectiveness of this feature, or any true dust collection system for that matter, it's achieving the highest amount of CFM flowing at the tool, or to be more specific in this application, the blade. For my design, I'll be using 4-inch duct for the overarm. This will actually complement the already existing 4-inch hookup at the cabinet, but dual 4-inch hookups have almost the same cross-sectional area as one 6-inch hookup, and my system is designed to run with 6-inch duct, so this is key. I'll talk about this in more detail towards the end of the video, but I can say this is a lot better than using 2-inch duct you see on some of the current models available for purchase. Along with maximum CFM, I wanted to include a few handy convenience features to assist in the ease of use. And of course, some safety features as well, because that's important too. So in addition, the hood needs to be clear so I can see the blade and the cut that I'm making. Next, the height of the hood off the tabletop needs to be adjustable so I can accommodate different thickness materials because I like options. And last, I want the ability to swing it out of the way when it's not being used. These are nice to have for some cuts, but other times it isn't completely necessary. I would say at this point in time, I had my design about 80% complete, and the mock-up allowed me to get my final design measurements and to tweak any oversights. The first item to build is what I'll be calling the hinged mounting bracket. This is kind of the heart of the project. It's what holds the overarm assembly to the nearby column and allows it to swing out of the way. I did my best to keep this as compact as I could, but I was limited somewhat by the fact that I'm using 4-inch PVC, 4-inch flex hose, and it will need to swing upwards. I cut this window out of one of the sides to accommodate the hose and its path to the hookup at the main line. But this is one of those times when designing in the digital work environment versus real-world installation is hard to fully plan. With how the hose bends and hangs, the window proved not to really be necessary, but I realized this a little too late in the game to justify a change. It doesn't really hurt anything being there, but for the curious minds, one might ask the reason for it. So yeah, it's one of them happy little mistakes. In order to make this arm rotate up, I designed and 3D printed a hinged pipe clamp. The rotating axle consists of 2 ¼ bolts and oversized holes in the lower half of the pipe clamp to receive brass bushings. This will prevent premature failure with use. The clamping action uses 4 6-inch ¼ bolts to allow the 2 halves to bite down around the pipe. Honestly, 4 is probably overkill, but I like the symmetry. I made the saddle to help support and capture the weight of the assembly when it was in operation. This would certainly be more effective if it was mounted further out, but this ties back to keeping it as compact as possible. With the mounting bracket installed and some scrap pipe fixed into the rotating pipe clamp, I started building out the dust hood assembly. Due to the size of the parts, it required me to get creative and print them in multiple pieces that could then be easily assembled to finish out the final product. I used a combination of these puzzle piece tabs and a dovetail-like joint you'll see in a future part. This makes it simple to ensure all the parts can be lined up correctly during the assembly, along with adding some strength. All of the printed components are made from ASA filament, and I've really grown to like this material due to its strength and the post-process finishing options. It's closely related to ABS and allows me to assemble it with ABS cement, which ultimately welds the pieces together. Another cool thing is it can be joined together using a product called Weld-on-4, which will be important when I get to installing the polycarbonate faces. To get this hood enclosed but maintain adequate visibility, I used Lexan or polycarbonate. I believe Lexan is just a brand name. The upper face/nose required a very specific bent radius. To accurately achieve this, I printed a template I could then transfer to several pieces of 3/4 inch MDF to create the bending form. I've been down this road before and tried winging it, but the outcome had less than desirable results. So even though these steps may seem like overkill, it gave me a damn near perfect result. This jig was important because it accounted for the 93 thousandths thick piece of polycarbonate, and I guess one perk with my old age is slowing down and nerding out on all these small but important details. I guess I'm not that old, I'm only 37, but some mornings I feel like I'm 70. Yuck. To bend the polycarbonate, I just used a heat gun and focused the heat only in the area that'd be bent, keeping good distance and constant movement. If you get it too hot, it'll deform and bubble. Then using copious amounts of clamps, I just sandwiched it between my forms and let it cool down. So yeah, all that pre-work for about a minute's worth of actual use. Totally worth it. To attach the polycarbonate faces to the frame, I used a weld-on 4. This product is designed to permanently weld acrylic together and is commonly used in the acrylic fish tank construction, and that's actually where I first learned about it. Back in the day, I had a saltwater fish tank obsession and I built my own setups, but that's a nerd conversation for another day. This apparently works very well for attaching acrylic to the ASA frame. Disclaimer, this stuff is very potent, so wear all your PPE, especially a mask, and do it in a well-ventilated area, or you just might find yourself taking an unwanted dirt nap on a concrete floor. Before cutting out and attaching the polycarbonate sides, I had to design and attach the air hookup plate to accommodate 4-inch duct. This was a battle of footprint restrictions and not sacrificing air volume. The workable width of the dust hood is roughly 3¼ inches, but I'm using 4-inch flex hose, and that's a slight problem. So to accommodate this, I lofted an ellipse to a cylinder to keep the maximum air volume unrestricted. And wham bam, I have this custom 4-inch hookup for the dust hood. And then using ABS cement, I made a complete mess gluing the hookup plate and the lower blank to the frame. Honestly, I tried to be clean about this, but I completely missed my mark. I'm sorry I'm a slob. To build the sides, I used some cardboard to create a stencil for building the template out of 3/4 inch MDF. And although this Georgia boot box made a perfect stencil, I assure you any cardboard will do. I actually sanded the cardboard to get it just right, and I don't think I've ever sanded cardboard before, but it was actually quite satisfying. I cut the polycarbonate side pieces slightly larger than my template to reduce the amount needing to be cut off at the router table. Okay, a couple pointers when using weld-on 4 is making sure to get your parts into position prior to applying it. It seems kind of backwards, I know, but trust me. This applicator bottle with the syringe is a must. This stuff flows like water. Then apply it to the seam and let the capillary effect pull it into the joint. This stuff sets up in a few seconds, so you really only have one chance to get it right. To fasten the dust hood to the 4-inch duct, I designed the support arm that will fit snug around the pipe and clamp down. This support arm was just a little too large to print in one piece, so I printed it in 2 pieces. To help align them during assembly, I used a large dovetail joint to allow me to slide the 2 halves together. And once again, I made a giant mess with the ABS cement gluing them together. Fortunately, it's easy to clean up with some acetone. To give the dust hood vertical motion and to accommodate different thickness material, the support arm has a rectangle hole through it to accept the vertical post. The vertical post will be attached to the dust hood. To lock the hood at the desired height, the support arm has a slot to accept a 1/4 square nut. This allows me to use a threaded knob to clamp the vertical post into position. I used a 1/4 bolt here, but I ended up building my own threaded knob for this and the clamping portion of the support arm. To attach the vertical post to the dust hood requires these link arms that snap into position on the vertical post and then are reinforced with a bolt. Then the link arms slide into the fittings on the dust hood and are secured with some 1224 hardware. Before installing and testing it, I had to cut in a 6-inch to 4-inch Y to tie this overarm dust hood into my existing dust collection system. I'm going to bypass most of the detail about this because it's pretty straightforward, but if you are curious, I'll have my dust collection install video linked in the description below. I go into way more detail about it in that video. With everything built, it was time to install it. I printed 2 of these 4-inch couplings, and they look pretty basic, and they are, except there's a slight taper to them so they fit perfectly into 4-inch sewer pipe and perfectly into 4-inch flex hose. The fit on these is so nice, I realistically don't even need hose clamps or screws to secure them. Once I got everything installed, I felt with the amount of time I put into this, I could make it look more professional. So I painted the overarm duct black and ditched the 8-year-old flex hose that I had laying around and bought new hose. I think that did the trick. It worked just fine before, but this really gave it the curb appeal I was looking for. Whew. Holy smokes, that was a ton of info in a short amount of time. Well, let's go check it out, run some tests, and see how well it works. Before I push some wood through and make some dust, I want to get some airspeed reads and calculate the CFM. If you don't care about the values, I'll leave a timestamp so you can jump straight to the comparison of me using this with and without the dust hood. The target numbers I'm trying to hit are going to be based off the first row of this published chart. There's 3 different standards for the ideal CFM flows at your tool that you should be shooting for. OSHA, the ACGIH, I'm not sure what that is, but it's more strict than OSHA, and then the even more strict, the Medical Euro recommended standards. These standards are to ensure that you have good fine dust collection to protect yourself, and I'm not talking about the big chips that are easily visible, but the small ones that are very hard to see or if at all. But I thought this would be a good way to put into perspective how well or bad my system actually works. The first row shows the values for a standard table saw, and the desired reads are both for the cabinet hookup along with the overhead dust hood flows. I'm shooting to be on par with the OSHA standard, but hopefully better, so I need at least 350 CFM flowing through my dust hood. The first couple tests I did are right where the 2 4-inch ducts hook into their locations, starting with the 4-inch at the back of the cabinet. I got an impressive 7,732 feet per minute, giving me 674 CFM. I'll take that. At the hood I got, damn it, this was not planned and this was actually the second time it happened to me. Let's try again. So right at the 4-inch hookup on the hood, I got 6,430 feet per minute, giving me 561 CFM. I got to thinking and wondered if maybe I should be taking these reads right at the bottom of the hood, but I couldn't find any write-ups on it, and I also wasn't sure how I'd correctly calculate that. The area of the opening on the dust hood is very close to the cross-sectional area of 6-inch duct, but the hood connects to 4-inch duct, so I'm not sure the best approach to this. But out of curiosity, I did a couple tests, and I used the area of the hood opening and the airspeeds. I took 2 reads and kept my anemometer about flush with the opening, one towards the back, that's the closest to the hookup, so I knew the reads would be best there. The second was more towards the front, and I knew the reads wouldn't be as great there. Towards the back, I had airspeeds of 3,185 feet per minute, giving me 859 CFM. And at the front, I had airspeeds of 1,394 feet per minute, giving me 376 CFM. Alright, so really quick, I got lost in my notes when I was doing my voiceover and I misspoke with those 2 values. The ones I displayed were the accurate figures. And the reason why I did that is because obviously if I take my reads right at that 4-inch hood, I'm going to have the highest airspeeds and the best CFM flow. But I was curious to see what that air did once it got inside the hood. So I took those 2 additional reads to kind of give a more accurate representation on what's going on. And with that, I feel like either way, I still have got great flows to this hood and they're on par with all the figures on that chart. So with that being said, let's cut some wood and see how it picks the dust up. I feel like the best way to visually show the performance will be doing a series of edge cuts on 3/4 inch MDF. I'll do 3 cuts without the hood and see how much dust accumulates, and then I'll do 3 cuts with the hood in action. After doing 3 cuts, you can see how much dust it produces, and that's still with my dust collection running and pulling from the cabinet. I actually did 4 cuts with the hood in place because my first cut was a little too far in and I didn't think it was a fair comparison, so I kept everything the same and just did 3 more cuts. There's only a couple sprinkles on my muffin top. One safety consideration I'll have to make is with my plywood zero clearance insert plates. If I set the height of the hood to anything less than 3/4 inch off the table height, it will suck the plate right out of the pocket, so I need to add some magnets to my insert plate design to correct that. Alright, so this was hands down probably the funnest project that I've worked on to date. I probably say that after every project, but this one was truly a blast. The amount of moving parts, the creativity involved to get it to work the way I expected it or wanted it to then getting to this end game where it works awesome. All the flows are on par with the figures in that chart that I displayed, and I'm glad I built it. Now, I've had a few people reach out and ask if I was going to make my design files available for download so you could print your own parts, or if the parts themselves would actually be available for purchase so you could kind of replicate the same setup in your shop at home. And just let me know down in the comments. I want to see what kind of interest there is for that. If there's a high enough demand, I can definitely make both those options a possibility. So just let me know down below. Along with any other questions that you have, I'll link my reference material for all my flow calculators and duct design. Bill Pence's website is a heap of knowledge for everything dust collection and how to set these systems up, whether it's just laying duct out or building your own system from scratch. So I hope you guys enjoyed it. And like always, the shop's not going to clean itself, so grab a broom and I'll see you guys on the next one.